Okay, so this is the point we got yesterday, right? So in particular, these guarantees, as described in this drawing, the following fact, right? So graphically, what we are saying here is that if you consider, sorry, if you consider the differential equation associated to residual neural networks that we have called the neural differential equation, because this is simply a differential equation and it has a neural structure due to the presence of the sigmoid nonlinearity. In particular, when the nonlinearity sigma is the ReLU, right? Using the constructive inductive arguments that I presented yesterday, you can show that the system has a very, very ambitious and distinguished property of simultaneous control, in the sense that when you give me n different initial points and n different final points, whatever n is, so n is arbitrary, and please recall that capital N here does not have anything to do with the dimension of the Euclidean space, right? So we are in dimension D, X is the state, is in dimension D. This is the number of, for instance, agents interacting on a network, D, right? And now I consider n possible trajectories and possible configurations. What I'm saying is that we can always find one single control B of t, A of t, and W of t, so that each of them, right, goes to the allocated point, right? Of course, there are a few remarks to be done, right? You see that how x1 goes to y1, x2 goes to y2, x3 goes to y3. Of course, the first remark to be done is that in order for this to be possible, right? So these are, so here we write arbitrary terminal states, but they have to be all different, right? So of course, I need the terminal states to be different, right? Because assume I have decided that in my control problem, in my simultaneous control problem, I want x1 and x2 go to the same destination, y1. Why that is not possible? Why I cannot take with this neural ODE system, despite this simultaneous control property, why I cannot take two different initial configurations and drive them to the same final one? Do you have a hint of why this cannot happen? Any comment on this? The reason is very simple. If two different initial data will get to the same final configuration, for instance, because I have another trajectory doing this, I will be breaking the uniqueness of the solutions. Yes, unique solution. Thank you, Matt. I will be breaking the property that for a Cauchy problem associated with an ODE for which the nonlinearity is global ellipses and the dependence on time is, say, measurable and integrable, right? We have the uniqueness of the solution of the corresponding Cauchy problem. If I will solve the problem backwards in time, right, I will be in a situation where the y1 will have to lead to two different trajectories, one going to x1 and the other one going to x2. And this is clearly impossible. So this can never be achieved, right? I will never be able to drive, you know, endpoints to end locations unless they are different. Now, of course, the distance here, y1, y3, can be very close, right? The only thing I need is the, they to be different. Now, when you look to the proof I have done, however, you realize that when you start, putting very narrow distances, when you put very narrow distances among points, if you analyze the proof we have given here with piecewise constant motions, you realize that, of course, if the distance is very, very, very small, when you decide to act, for instance, pushing the north hemisphere to the left while the south hemisphere is frozen, you will need to wait longer, right? Why? Because the distance is so narrow that you really need to see the separation emerging, okay? Then eventually, we have seen that if I need longer time, when I rescale time to 1, this is having an impact on the control, which is of the order of the time interval, right? So we have said that, whatever you can do with the control WT in the time interval 0 capital T, right? You can do it with the control capital T times WT, sorry, in maybe also a change of variable here, right? Capital T times WT in the time interval 0, 1, right? But the fact that you are shrinking the time interval from a long time horizon capital T into a short time horizon 1, in particular makes that the amplitude of the control is multiplied by capital T. This is in agreement with common sense, right? So longer time horizons require a smaller control, shorter time horizons require larger controls, right? Okay. So then the fact that, if you decide that you want to control, sorry. If you decide that you want to control to terminal positions that are very, very, very close, this will oblige you to use controls of large amplitude, right? Because as we said, when the data to be controlled are very close, we have to make distinctions using hyperplanes and the corresponding, say, strategically chosen flows, let the time interval to be long, or in other words, if you fix the time window, use controls that are large. And this is in agreement with common sense, right? Because what is the typical expectation you have, right? Is that if for a control system, you ask, to get to a configuration which is impossible, right? Then you will say, no, you cannot get there. The system is not controllable to that final configuration. So, don't even try, right? You will never find a control driving to that final configuration. And then you say, well, it doesn't really matter. Rather than getting to this final configuration for which there is no control, let me get epsilon close. Because if epsilon is very small, being epsilon close is fine for me too, right? So is that okay? So we have to start the class at 8 a.m., but probably we don't start at 8:00 a.m. Maybe we start at 7:59 or 8:01. Okay, so nothing is really exact. And then you say, don't worry. If for any reason the system is not controllable to a final exact configuration, I will control to an epsilon neighborhood. But what do you think is going to be the phenomena that I will observe when I try to get to an epsilon neighborhood of a state that is actually not reachable? When you push epsilon down to 0, what do you think is going to happen to the controls, typically? Right? So the question is, what do you think it happens to the controls when I try to get epsilon close to a target that is really not reachable, not attainable. How will the controls behave? You try to get very, 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 very close of a configuration that is impossible to be achieved exactly. Then the controls have to blow up as epsilon goes to 0, right? Because otherwise you can argue by contradiction. If when getting epsilon close, all the controls will be uniformly bounded, I will pass to the limit weakly in the corresponding topology, right? So for instance, if the controls are uniformly bounded in the space of bounded variation, right? I will pass to the limit weakly in the space of bounded variation, right? This will allow me to, weakly in the limit. This will allow me to get by compactness of Sobolev embedding some compactness in LP. I will pass to the limit in the equation, and I will see that the limit control gets, epsilon close, epsilon going to 0, it gets exactly to the target. And this is impossible because we said the target is not reachable, right? So then in here, there is some justice, right? So if something is not achievable, you can get it epsilon close very often, but of course the price to pay, the cost of controlling the system blows up when epsilon goes to 0, okay? So then this is to say that actually the fact that you have the simultaneous control property, you should not abuse of it, right? Because, you can produce this kind of, transport maps from a given initial configuration to a given final configuration. But if you really want to, to make things very tight, then the cost of control will be very large. The same will happen if X1 and X2 are very close. This is just because of the well-posedness properties and the Gromval estimates for the ODE. If you take X1 and X2 that are very, very, very close, and then you ask the two trajectories to get to destinations that are very far, it means that you have to use controls that are very large, right? Because, in a nonlinear differential equation, right, the distance of the two trajectories, right, can only grow according to the worst case estimate that the Gromval inequality provides. Okay, so then, the statement says, indeed, for such a neural differential equation, you can take n initial data which are different to n final configurations which are different, right? And the number capital N of such trajectories is arbitrary. But of course, if you start, forcing the system so to make impossible things like getting initial data which are very close or targets that are very close, then the size of the control will start growing. And as you know, in practical applications, always beyond a given threshold, telling that you have controllability with a cost that is unaffordable, with controls of a size that you cannot realize because your actuator is really unable to implement such an action. In fact, this controllability property is not realizable in practice. Okay? Or in other words, using a scaling, we could say, no problem. Wherever needs, controls of size very large in time 1, I can make it with controls of size 1 in very long time intervals. Yes, fine. But then there is also a price to pay. Is that in order to achieve the target of your control process, the time horizon might be too large, right? And then if we are, for instance, finishing this course next Monday, right? I can plan to do many things, but if I'm not able to do it in the time interval 0 capital T, which I am given up to next Monday, I will never be able to achieve the goal, right? So then in practical applications, you have always to pay attention to the cost of control. And therefore, whenever you have a property like this telling you that the system is controllable, which actually means, our interpretation of the controllability is the classificability of the system, right? Saying you can take many different data and classify them according to the labels, right? That's fine, but you have also to think on how expensive this is going to be, right? And then I'm not sure I said that the other day, right? You remember that how did we get to this neural differential equation? We said we started with Sivenko, in which he is accumulating, you know, building a neural network with one single layer, but you know, which is very wide, right? And then we said, rather than doing this with a very wide one single layer, I will distribute this work along different layers, building a deep neural network. And in order to understand better, you know, how this deep neural network, which is a discrete incremental dynamical system, behaves, I look to this neural differential ODE, which is the limit as delta t h, small h in our notation of the deep neural network goes to 0. And we go to this neural differential equation where I am comfortable and I can apply, right, these techniques of ordinary differential equation control. But clearly, once you have this result, if now you move from this time discrete time continuous scenario to time discrete with delta t small enough, clearly, because of the classical results in numerical analysis that tells me that if I take a numerical scheme which is convergent, like Euler or multi-step or Runge-Kutta, the classical numerical schemes in the theory of ordinary differential equations, because I know that the numerical scheme converges to the actual continuous trajectory of the system, right? I will know that whatever I can do here exactly for the, you know, deep discrete neural network, for the ResNet, the residual network, I will be able to do it too in an approximate manner, right? And as I said, doing approximate controllability is more than sufficient in order, for instance, to achieve classification, right? Because as we said yesterday, when we are dealing with classification, we have different sets and the goal is to simply drive, right, different classes of, you know, data to the corresponding sets. I really don't need to bring them to the same point, something that simply will be a bad mathematical modeling because it will make the problem, you know, unsolvable or extremely expensive in the sense that the controls or the time horizon are too long while I don't really need it. Okay, very good. So now this property of simultaneous controllability of the neural ODE, right, which can be as a corollary guarantees the classification property of this neural ODE, which is, you know, the central topic in supervised learning, can also be understood in the context of transport theory. You remember we said in the introductory lectures that there is one of the main applications of control and optimization is optimal transport that was introduced by Monge, Gaspar Monge, and then later developed by the Russian economist Kantorovich. Nowadays we say optimal transport of Monge, Kantorovich Monge, right? Of course, this is related also to optimal transport, right? Why? Because, you know, if I am able to bring x1 into y1, x2 into y2, and x3, you know, into y3, right? If I will allocate the mass m1 to x1, this mass m1 will be transported to y1, the mass s3 m3 to y3, and the mass m2 to y2, right? So how is this done? Well, simply thinking that a way of representing a distribution of masses given by the mj's located at the points xj, right, this, right, can be simply represented by a Dirac delta, right? So if I take this n atomic measure, which is taking, you know, just the sum of the Dirac deltas at xi multiplied by mi, right? Then what this theorem is telling me that because I can take xi to yy, I am able to take the mass mi that was located in x1 and place it in y1, right? So these are like, you know, students finishing the bachelor program, right? There are 40 of them in the class, 40 students, x1, x40, they decide to study master studies and a PhD. Probably they don't remain in the same institution. Some do, but some others move to other institutions, right? This introduces a transport map, right? That takes this population of 40 young mathematicians that from, you know, the university today, Jilin, they move to, right, to different master programs, including those of the present institution, but some others as well, right? Okay, so this is a transport map. We are transporting the mass and redistributing this mass, okay? You can, of course, think on, you know, you say, well, but in fact, what I would like is to take the mass here, M1, bring it to, you know, to the point Y1, but in the meantime, I would like to modify the mass M1 so that it becomes M1 prime. I will tell you, well, this is not possible in here, right? In here, I'm just moving the center of gravity of the masses. But the mass is being driven, right, along the transport map. So you will not modify the mass. If you really want to modify the mass, you have to pay a little price, right? Which is the price of making things epsilon close again, right? Like when I said there are configurations that are not reachable, for instance, 2 points go to the same point. If that were possible, it would be great because the arrival point will take the mass M1 and the mass M2, and the final mass at the arrival point will be M1 plus M2, but we have said this is not possible. This is only nearly possible, right? So then the only thing you can do in those cases is to say, okay, if you tell me that you want to transport mass, but also to redistribute the mass, right? So that one takes M1 prime, the other one takes M2 prime, the other one takes M3 prime. What you need to do is to take the initial point with mass M1 and split it into small points, I mean, in 2 points that are very close. So this mass M1 can be rewritten as, say, N1 prime plus M1 double prime. And then because this point X1 has been rewritten as two slightly different points, X1 prime and X1 prime prime, the two green points out of the red point, then you can allocate the mass M1 prime to X1 prime, the mass M1 double prime to the point X1 double prime, and now because they are different, you can bring them to a different destination as well, right? Okay, so then in this way, you see how not only you can transport mass, but you can also, right, redistribute mass while transporting under the condition that there is always an epsilon error at the arrival, right? Simply because of the fact that two initial data for an ODE that is well posed in the sense of Cauchy-Lipschitz cannot collapse exactly at the final time, right? Okay, so now you see that you could also do this with functions, right? So if you give me, for instance, and this is very much related to the theory of optimal transport, right? So here I'm not saying I'm doing anything optimally, I'm just saying that I can do transport of mass using the ideas of neural ODEs and neural networks, right? If you give me, for instance, a first distribution of mass given by rho 0x, and a second distribution of mass, ρ1x. So this is, for instance, the wealth in your city, how the wealth is distributed in the different, say, among the different citizens or neighborhoods in the city. And then you say, well, we are not happy with this distribution because there is too much accumulated here in the center, and we would like to bring more wealth, right, to the, to the peripheric points. And you say, okay, this is the new configuration we want in our town, right? This could also be, for instance, the density of cars. We say, oh, there are too many cars here. I like the center, the downtown have less density of cars, and then push the cars to the outside. How do I succeed bringing this initial distribution ρ0 into this final distribution ρ1? Well, if you ask me to do it exactly, it's going to be tricky, right? In particular, in this context where, I mean, for instance, collapses are not allowed by neural differential equations because of Cauchy-Lipschitz. But if you are ready to pay an epsilon price, then this is, you see, this is something you can do, right? Why? Because given some initial datum, right, ρ0, and some final datum, ρ1, now continuous functions of x, so these are density functions, so that the mass of both of them is the same, you can always divide, you apply the same principle as the Riemann, right? Or the Lebesgue decomposition into level sets as you wish. Here we do it a la Riemann, right? So I divide the variable x into a small, I do a partition so that I have small segments, right? I can do that here and I can do that there. And then I can take these segments so that the mass in here is equal to the mass in there, and the mass in here is equal to the mass in there. Of course, in order to guarantee that this mass is equal to this mass, and this blue mass is equal to this blue mass, because the profile of the function ρ0 and ρ1, the height is not the same, I will need to take intervals in x which are not identically long, right? But I can always find a partition so that, the n, here I will have capital N, right? Number of segments, right? Here and there is the same. And the total mass of each segment is the same. Why? Because the integral of ρ0 and ρ1 is the same, right? So once you have done this, you can easily realize that you can use, the principles before, so to bring this to here in an approximate manner. How do we see that? What is the idea? The idea is that, okay, so all these points have to go to one point. I can do it forward, and then I can also do it backward. Why? Because the ordinary differential equation is time reversible, right? This is the great thing of dynamical systems that are time reversible, right? So this is a trick that is often used in practical applications, right? So let me just make this small comment, right? Okay. So control of time reversible systems. Okay. So in particular, an ODE like this with, say, F, which is globally Lipschitz, is always time reversible. What does it mean? Well, it means simply that if you give me the initial datum x0, I apply Cauchy-Lipschitz, and I will get a trajectory which is continuous in time with values in Rn, taking the initial datum x0. But if for some reason you give me, rather than give me the initial datum xt, you give me the final datum x capital T, then I will also get a solution in the same class, right? So this will be continuous, but it will be also C1. But this time, x of capital T will take the value xt. What is the proof of that, right? The proof is very simple. If you have to show this equation, right? But now you have to do it in the backward sense of time, right? From t equal capital T to t equal to 0. So we can reduce this final time problem to an initial value problem by doing what? Well, I will simply define the trajectory yt equal to x of capital T minus t. And what's going to be the ODE, right? What's going to be the ODE associated to y is going to be y prime of t equal to minus f of yt u t minus t and y of 0 equal to x capital T. But if f is global ellipses, minus f is global ellipses, and then you can apply the same Cauchy-Lipschitz result. So in the context of ODEs, right? In the context of ODEs, we can use time reversibility or time inversion. This is also an idea that is very much used in inverse problems, right? Okay, so what does it mean? It means that, for instance, assume that you have already proved a result saying that, okay, given this system, I was able to show that there is a control U such that x capital T is equal to 0, right? Okay, so you were able to get to x capital T equal to 0. X capital T equal to 0 is typically one of the targets we look for. So this is particularly relevant for nonlinearities in which f of 0, 0 is equal to 0. Why? Because if you know the nonlinearity f is so that f0, 0 is equal to 0, right? You can always say that for the control u equal to 0, right? X equal to 0 is a steady state, right? And we are particularly interested in controlling the system to a steady state. You can, of course, control a system to a moving trajectory. This is like when you see in the movies, right? That the train is passing, and then you see the passenger that gets late to the train station, then runs and is able to jump onto the train. Well, you see that in the movies. In practice, this doesn't happen that way, right? So you are not normally allowed to jump onto a train that is, moving, especially if it is a train, a fast train, 300 or 400 kilometers per hour. You can only do that in the movies, right? So you cannot do this on real life. Okay, so it's in principle possible to, to control, to track into a trajectory that is moving. But in practical applications, most often we are interested on controlling into a, equilibrium configuration. So I am sitting here. Now I change my equilibrium configuration, right? And I change here, right? And I move from a sitting position to another sitting position. I have moved from one, say, initial configuration to a final configuration, which is a steady state. Okay? But then oftentimes, you prove this first result about the controllability of the system to the 0 equilibrium, but then, the requirements change, and then people ask you, could you please control the system from, say, x0 into rather the terminal state x capital T? So it's fine that you were able to control to 0, you know, but today we want the target not to be 0, but to be xt. Right? This is like the hidden system in the building. You say it's very good that, you know, the hidden system allows you to drive temperature homogeneously to 20 degrees. But today the requirement is 19 or 21. Can you do that? And you say, well, I don't know. I mean, I did it for x0. I have to do everything again. Do you really need to do everything again? No, because you can do the following. You can divide the time interval 0 capital T into 2 pieces, right? And then what I can do is that from x0, I can drive the system to 0. And then if the target is xt, I can also do control the system in the backward sense, and I can drive the system from, say, the terminal condition to 0 at a time, say, t over 2. And when gluing these two trajectories, right, you see that we move from x0 all the way down to xt. Of course, you have to pay attention that here I have, right, divided the time interval into 2, right? 0t now has become 0 t over 2, and the length of the second time interval will also be capital T over 2. But as we know, in most finite dimensional systems, right, what you can achieve in a time window, you can achieve it also in a shorter time window with larger controls. Of course, this will oblige you to use larger controls, because after all, you are producing a deformation that is not going from x0 to 0, but is going from x0 all the way down to xt, right? But this is feasible under the condition that you use, you know, larger controls. Or in another manner, you could also say, well, whatever I could do in time, you know, capital T, to move from, say, x0 to 0 by means of a suitable trajectory. Now, you could also argue differently, and I say, okay, I divide, you know, I increase the time by, you know, t. So I pass from the time horizon 0t into the time horizon 0 to t. And then if you ask me that I have to go from x0 into xt, then I will do it in 2 steps. In the first step, I will move from x0 into 0. And then in the second step, I will do it backwards, moving from xt into 0. And the gluing of all these two, say, trajectories, right? The gluing of these two trajectories provides a trajectory that goes from x0 into xt, right? Now in the time window 0 to t, but hoping that the amplitude of the control is the one that you got for the time interval t without amplifying the control. Okay, fine. But you see, when I am using this argument, I'm saying implicitly, I'm using something that I didn't actually say. I said that in the context of the Cauchy problem, of course, right, you can solve the equation backwards. Why? Because when you try to solve the equation backwards, it's the same as solving the equation forward for the nonlinearity minus f. It's just changing the sense of time. Therefore, it's just changing the sign in the time derivative that you can also, you know, reflect on changing the sign of the nonlinearity. But if f is global ellipses, then minus f is also global ellipses. So my question is rather, this doesn't change the controllability of the system. Is it true that if the system x prime plus ax equal bu controllable? My question is, does this imply that the new system y prime minus ay bu is also controllable. So the fact that I'm changing the plus sign into the minus sign, is it true that it preserves the controllability properties of the system? And in case it is true, what will be the proof? Do you have a guess for this? Ma says yes. What will be the proof, Ma? Kalman rank condition. Very good. Very good. So you see that indeed, you know, AB to be controllable means that the rank of B, AB, A n minus 1B is n, right? But, you know, this also implies that the rank of B minus AB, A squared B, up to minus 1 to the power n minus 1, A n minus 1B is equal to n. And this is equivalent to minus AB being controllable. Okay? Very nice. So then you see that in this setting, where I was transporting an initial mass into a final mass, right? I can do it, right, with an epsilon error, in particular, because I can simply say classification means that these points can go to, you know, an epsilon neighborhood of this one. These other points here will go to this epsilon neighborhood of this one forward, the other one backwards. And when I match, right, I have a transformation of the initial mass into the final mass, right? So then we see that, you know, out of these elementary results on the simultaneous control of the neural differential equation, I can do neural transport with an epsilon error. What does it mean? Neural transport is the transport of mass. But now I'm not doing, as in the theory of Monge-Kantorovich, optimal transport. They were doing optimal transport in the sense that the transport map is built to be optimal with respect to some cost. This is something very natural in practice, right? You want to move from one apartment to another, but you want to do it in a minimal time and you want to invest the less possible money, right? Then if you take these two criteria into account, as we described the other day, then you have to decide whether you do it with your car. Maybe with your car, you have to do many trips because the car is small. You have to do many trips and then it's expensive from the perspective of time cost. Maybe you can rent a van. Okay, you have to pay maybe 100 euros for renting a van, or 200 euros or 300 euros. Okay, it costs a little bit more in terms of money, but then you can put everything on the van and make the transport in a much shorter time. Then the question is whether you can afford 4 days for moving, or you prefer to do it in just one afternoon paying 300 euros. Depends on the person and the conditions, right? So optimal transport means transporting optimally. So for us, we are not talking here about optimal transport, we are talking about neural transport. Why we talk about neural transport? Because we are doing it, you know, out of our understanding of neural differential equations, right? Okay, but what is the object that is hidden in all this discussion? I said, I take the neural ODE, I take initial data and final data, I see them as Dirac deltas, right? Or atomic measures. I can modify a little bit the initial and or the final Dirac atomic measures so to guarantee epsilon control. This can be interpreted in terms of the transport of mass. What is the new differential equation that is hidden in this discussion? Does this remind you something? In the theory of partial differential equations, what are the classifications? The classical classification is elliptic, parabolic, hyperbolic. The most classical example of hyperbolic equations are the wave equation. Yesterday we also mentioned with Professor Kai other models like the Maxwell equations, the elasticity equations, and so on. I will come back to this later today, right? But then there is even a simpler model, is the pure transport equation. And we know that pure transport equations can be related to the characteristics of a differential equation, right? You remember that, right? So you know that if you ask me to solve this Cauchy problem, right? Given a velocity field, you ask me to solve this Cauchy problem in RD cross 0t with an initial datum f0 of x, right? The question is very simple, right? Because I can say, listen, if you want to solve this transport equation, the only thing you have to do actually is to compute the characteristics. Right? What are these characteristics doing? Well, you are taking, you know, RD, and then out of any initial possible point, x0, right? You are building one trajectory and then another, and then another, and then another, and so on, right? And then what the equation does simply is to guarantee that, you know, the density, sorry, the density F is constant along trajectories, right? Along these characteristics. Why is that? Well, it's very simple. Take the time derivative of this quantity, right? So this quantity is, you know, the value of F, the solution of this problem in xt at time t. My claim is the value of F at this point in time t is going to be the value of f0 at x0 at time 0, right? Why? Because when I take the time derivative of this quantity, right, if I compute the time derivative, this will give me on one hand the time derivative of f with respect to t, so ft, but it will also give me the gradient of f multiplied by the derivative of x prime t. And the derivative of x by construction is the velocity field, right? So in this way, these are the characteristic lines, and these characteristic lines are completely characterizing how the mass is being transported along this transport equation. You see that there is also some natural hypothesis that emerges in order to apply this theorem, right? Why? Because if I want this system of differential equations to be well posed with respect to the velocity field capital V, you will assume capital V to be global ellipses. So if capital V is global ellipses, right, then you can show that the transport equation is well posed simply because the Cauchy problem for the characteristic lines is well posed. If you relax the regularity of capital V, right? For instance, if you just use the, you know, Peano's theorem, right? Saying that if V is continuous, then there is a solution, but there is not uniqueness, then you will have the same result at the level of the transport equation. You will be able to find one solution of the transport equation, but you will lose uniqueness either, right? And then there are many notions like Filipov solutions. There are the theorems by Di-Perna-Lyons on, you know, solving the Cauchy problem almost everywhere, which allows you to get deeper into the interplay between transport equations and ordinary differential equations, right? But in our case, the ordinary differential equation is the neural differential equation, which is global ellipses, and there is no problem. We are really dealing with the neural transport equation, let me see where it's written, right? It's here, right? This is the neural transport equation I am considering, right? So everything I said about the neural differential equation can be reinterpreted, rewritten as information on the neural transport equation. And the theorem we have proved allows me to guarantee that if now you give me this kind of neural transport equation, which is a hyperbolic PDE, and you allow me to control on this red velocity field, controlling the velocity field, I can transport the mass ρ0 as close as I like to ρ1, right? I can transport the mass ρ0 into ρ1, right? Up to an epsilon error by just a suitable choice of W, A, and B, okay? Is this optimal transport? No, I don't tell you it's optimal because I know the cost will be tricky because I need to use the results on the controllability of the neural ODE. But I will tell you something that the theory of optimal transport in principle doesn't say, right? Because here, what I'm telling you is that, listen, you don't need to use all possible velocity fields. It is sufficient for you to use velocity fields that have this very specific neural structure. So the velocity fields I use are simply the multiplication of WT times the sigmoid applied to ATX plus BT. This is why we call it neural transport, because we perform the transport of mass using neural velocity fields. So you see, this is not so surprising either, right? Because you recall, Sivenko said, every function can be approximated by neural networks. So in some sense, you have to expect that whatever you do with functions, in particular optimal transport, according to the theory of optimal transport of Monge-Kantorovich, this version of looking to optimal transport as the control through the velocity field of a transport equation is in particular due to Benamou and Brenier much more recently, right? If you are able to do control on the transport equation through the velocity field, then you could claim also Sivenko and say, oh, listen, but whatever you have done with a general velocity field, you could do it with a sigmoid, I mean a neural network, because the neural network is dense up to an epsilon error, right? And this is precisely what we are doing, right? But rather than claiming the result of Sivenko that was proved by Hambanach, here we are doing it in a very, very, very constructive manner, right? And this is actually the way in practice you will proceed. I mean, you have to transport the whole, belongings you have in your apartment, then you will divide it into pieces, you will put it into boxes, and then you will transport the boxes to place them in the new place, and then you open the box again. This is what we are doing. Pack things into boxes, then move the box and open up the box to recover the belongings and place them in the new location. Okay, so this is something that is very important, which allows you to understand the link of the control of ordinary differential equations and the theory of optimal transport, right? Also in this context of neural constructions, where everything is limited to be of neural form, right? Fine. So then you see, in particular, using these ideas, you can really handle, more delicate problems of classification, right? So we do it here in a continuous setting. Assume you are given this configuration here, right? Now we are talking about continuous functions, right? So this could be for instance, the characteristic function of this red set here, right? So you have this kind of ellipse, right, or lentil here, right? This length here is red, right? And here I have blue, right? Sorry, here I have blue. Fine. So I can identify this with the characteristic function of this lentil here, on which I take the value, say, right, +1, and here 0. Right? You can think on this as being a characteristic function. And I tell you, well, listen, but these are clearly two different pieces of material that I would like to separate, right? And I would like the blue material to go here and the red material to to go there, right? So this is like when you are filtering the coffee. I mean, you get the liquid with the aroma, but you get the powder out, right? So you are filtering tea or filtering coffee. You separate the solid and the liquid, right? Okay, because you don't want to drink the solid, you just want to drink the liquid, right? So we are filtering, right? Separating. How can we do that? Well, you can use all these ideas, right, of neural control or neural transport control. There is always, if we are in the continuous setting, there is a small price to pay. What is this small price to pay? Well, is that, is described here. You have to do a small surgery, right? If you ask me to really separate the white and the red, right? I really need to, cut here a little bit, right? Through this white interface over there, right? So let me make just this small cut, right? This is like kids doing homework, right? So, you have to cut. You make a small, fracture here, correct? And along the perimeter of the red cell, then you can introduce this very, very fine neighborhood of the boundary. You agree with me that I can make this with a measure which is epsilon small, right? I can do that. Then if I modify this ρ0 a little bit by ρ0 epsilon, then I have some epsilon distance between the two sets. And once I have the epsilon distance of these two sets, I can start, this motion of points that we have shown, in the discrete setting, right? But here, extended to the continuous setting, in which I am moving bunches, chunks, clusters of points. And then in this way, I can start modifying the blue set so that it gets here, this contracts, until eventually I can put all this, say, mass concentrated in the 2 points. So you can do surgery, you can do image processing, you can do classification in a continuous context, you can do supervised learning after all. Okay? So this is an important link between neural control and neural transport, which is related to optimal transport and universal approximation as well. This is, of course, also a theorem about universal approximation, right? Because eventually, what I'm getting here is a function that is taking one value or the other. So I am making an, L1 approximation of the characteristic function of any set. And then if you make the L1 approximation of the characteristic function of any set, because simple functions, which are linear combinations of characteristic sets, are dense, then you are also proving density. So all this allows you to prove the density in L1 out of the neural control and the control of the corresponding neural transport, right? So then what I'm saying here is that, sorry, what happened? Oh, here. Neural control, which is the same as the control of the neural differential equation, implies neural epsilon transport, right? Epsilon, because there is always a small error due to this interface that I have drawn here, right? And this applies the universal approximation, right? So if you wish, we could say, well, we have a different proof of the theorem of Sivenko using control theory. You will tell me, well, this was much more complicated. I prefer the original proof of Han Banach that was straightforward. Me too. I mean, if you just want to prove, you know, the universal approximation theorem, you do it using Han Banach as Sivenko did. That's beautiful and it's very compressed, it's very conceptual, it's very nice. If you do all this, all we have done here is because you are really interested on the dynamical system aspects, right? And you want to link, you know, all this theory with the classical control of dynamical systems and also optimal transport. Okay, good. So do you have any question on this topic before we jump onto something else? Are there questions on the chat? Okay, so let me then move to another very important topic, which, well, definitely arises in classical control of mechanical systems, but that you see, we have been led to consider it here also spontaneously because of this link between neural ODEs and neural transport equations, right? So let us then briefly discuss this topic of the control of infinite dimensional systems, right? So this is a subject that has been very, very active in the last, say, 50, 60, 70 years, right? So for instance, you have this very basic result by Kalman in the 50s of the A-B control condition, right? That was then extended to the nonlinear setting using Lie brackets, linearization, and so on. Then there was the theory of the Lyapunov equations for, say, the feedback control and the stabilization of systems. There is a huge literature on the control of finite dimensional systems because they are so relevant, right? In biomechanics, in robotics, in you know, on the you know, solar system, rockets to the moon. I mean, there are so many applications in astronautics, all kind of chemical processes, biological processes. This is a huge field, right? Okay. Actually, as I said in the beginning, you know, you have a mathematical theory of control, but then there is also a whole field of control engineering, right? Where when you go to one of these yearly celebrated conferences, you have thousands of participants, many sections addressing the different aspects of the theory. Deterministic, stochastic, time continuous, time discrete, switching system, right? Actuators, sensors, design of systems, you know, model reduction, observation, there are, you know, stabilization, there are plenty of subfields, right? Okay. In the math classification of the American Mathematical Society, right? In Math CNET, if you look to the math classification, I think control system is section 93, right? But you will encounter elements also of control in other sections like optimization and the calculus of variation, which, as we said, are all very closely related, right? So in the math classification, you know, you have to sometimes watch to these three sections: calculus of variation, optimization, system theory, and of course also the section on ordinary differential equations and partial differential equations, where you often have a section on control problems, right? Okay, this is a very broad field. But it was initially developed for, say, finite dimensional systems, ordinary differential equations, right? And then it was maybe in the 60s, you know, when the theory of PDEs, the modern theory of PDEs was well established, people said, well, but in the context of continuum mechanics, I should also consider this, right? So we have seen, for instance, this simulation of the of the regulation of water, you know, vibrating oscillations of water in a canal, right? We said, well, I mean, if you can simply let the force of gravity to do it, then it can take very, very long. If you are building a navigation system, you really need to, you know, minimize the waiting time, you know, for the boat to go from one segment of the canal to the next segment. And you need this stabilization process to be much shorter. If you think on the model for this, you will say, oh, but this is a hyperbolic system. This is the, you know, the shallow water or the Saint-Venant equation. This is definitely not an ordinary differential equation problem. It's a partial differential equation problem. If you think on the regulation of heat, you know, in a building, you say, oh, but the heat equation is also a partial differential equation. If you are talking about vibrating structures, for instance, under the action of a seismic wave, these are elastic structures. This is the system of elasticity. If you think on electromagnetic waves, this will be the Maxwell equation. If you think on applications of laser beams for controlling and design of molecular systems, this is the Schrödinger equation. Navier-Stokes, all kind of models, they look really like finite dimensional. And then people started to think on this, right? And the first question was, right? How can I, so now in the case where X is in Rn and U is in Rm, typical application being M less than N, we know that the Kalman condition is equivalent to the controllability, right? And it simply says, as we were writing a few minutes ago, that the rank of B, AB, A n minus 1B is equal to n. So then my question is, what is the extension to infinite dimensional systems? Okay, so what will be the simplest possible infinite dimensional system? Well, it's very easy to think on this, right? So what is the simplest possible infinite dimensional space? So I can go from Rn into little L2, right? Little L2 is the Hilbert space of sequences that are square summable, right? And this is a Hilbert space because if you ask me to take the scalar product of two sequences in little L2, I know this is the sum of AJ, BJ, and I know that this sum converges, right? Because of this inequality, right? What is the name of this inequality? Does someone know? What is this inequality? Cauchy-Schwarz. Thank you, ma'am. Yeah, this is true in every Hilbert space, right? And now, what is L2? Well, L2 is kind of an, it's hard to draw, right? But it's kind of an idealization of, right, Rn when n goes to infinity. It's an infinite dimensional space where you have infinitely many directions that are mutually orthogonal, right? So how do I see this? Well, I can take EJ, the vector EJ in the Hilbert space. L2 is the one, right, that is taking all values 0 except on the jth. And then you give me the EL, in which, you know, the one is placed somewhere else in the Lth component, right? And when I make the scalar product of EJ with the scalar product of EL, right, I get 0 when J is different from L, right? Why? Because I have to multiply, you know, these vectors component-wise. So 0 goes with 0, and then the only chance in which I could get something different from 0 will be that the one here is sitting in the same location, in the same index as the one here, right? As soon as J is different from L, they are mutually orthogonal. So this is a Hilbert space, and it's infinite dimensional because I have infinitely many vectors that are mutually orthogonal, right? And actually, the distance between these two vectors is going to be a square root of 2 because of the Pythagorean theorem, right? So, and this you see how, you know, for instance, this also gives you the prototypical example of why in an infinite dimensional space, bounded sequences are not necessarily having convergent subsequences, right? Because, you know, the sequence EJ, when G goes to infinity, is a sequence in L2 so that all the norms of each vector is 1, but the distance between any two different vectors is a square root of 2, right? And then this implies that there does not exist a Cauchy subsequence. Okay? So in particular, because this is a complete space, there is not a subsequence that converges strongly. However, as you know, EJ converges weakly in L2 to what is the limit of this sequence weakly in L2? What is the weak limit of this sequence? What do you get if you start jumping? Imagine you are jumping in this, you know, you like go to, you know, to the gym and to exercise, and you like jumping. So you jump from one vector to another, and then to another, and then to another, and then to another, and then to another, right? In every jump, there is a distance, a square root of 2. What happens to you? You will be exhausted. You will be jumping and jumping and jumping, and you will never end. So the limit will be 0 energy, right? So the weak limit is 0. And the weak limit is 0 is because the weak limit is simply looking to the projections into finite dimensional spaces, right? And looking to the projections on the finite dimensional spaces is like, you know, making this vertical projection, right? That we often use also on data sets in machine learning, right? I look to the first component and then to the second component and the third component, and you see that component-wise, the sequence goes to 0, because what is the sequence component-wise is 0, 0, 0. There is a 1 once, and then it's 0, 0, 0 again forever. So the weak limit is 0. Okay, so this is the Hilbert space. Then I could say, okay, then in little L2, let me write this system, right? I could consider this system in little L2. Right, so now x0 is in little L2, x2 is little L2. A now is a bounded operator from little L2 in little L2. It could be seen as an infinite matrix, right? Just the coefficients of this infinite matrix, the coefficients of this infinite matrix being so that you map an L2 function in an L2, a small L2 infinite vector into a small L2 infinite vector. Of course, this will always happen when A is of finite rank, right? If A is simply, right? If A will be something like this, in which you have a non-trivial block of finite dimensions and then 0, 0, 0, right? If this block was of size n, this will be like a finite dimensional system n times n. But of course, you can always make this to be non-zero, right? This to be non-zero, and make it decay fast enough so that, you know, A maps L2 into L2, right? And then you will have a linear bounded operator in the sense that, you know, you will be able to bound AX by the norm of A times the norm of X, right? So this is now an infinite dimensional system. There is no doubt. this is an infinite dimensional system, but the operator A is bounded. So I can still solve it, right? So I can solve it like, you know, xt to be exponential at x0 plus the integral from 0 to t exponential at minus s bus ds, no problem. And if you ask me what is the exponential at, I will tell you, well, I mean, if A is a bounded operator, A times T is a bounded operator, and I don't have any problem because, you know, this sum here, right? TAJ divided by J factorial, meaning the sum for J greater, than 0 of T to the power J divided by J factorial A to the power J, this converges in norm because of the Weierstrass majoration principle. Why? Because the norm of exponential at will always be less than the exponential of the absolute value of t times the norm of a. So the problem is well posed. The problem is well posed. And then people said, well, can I then say that controllability will be equivalent to the condition that the rank of B, A, B, A squared B up to A, N minus 1 B, and then I continue up to infinity is equal to infinity. This condition makes sense, right? At least I will be able to explain. I don't know whether this is true, that the controllability of the system is equivalent to this kind of rank condition. But if you ask me what the rank condition is, I can explain it to you, right? Because the rank being infinity, for me, it simply means that you can make the rank as large as you like, taking submatrices, right? And if you need very large matrices, you can, of course, get it out of here, because here I'm just writing infinitely many powers of A. And in this case, this makes sense because A is not a finite dimensional matrix. So I don't have a Cayley-Hamilton polynomial for the matrix A. I would rather have a power series expansion involving all the powers, right? Therefore, this condition makes sense. Do you think that this condition suffices for the controllability of the system? Do you think that the rank being infinity will be sufficient to analyze whether the system is controllable? Of course, the definition of controllability is the same, right? So no doubt. I mean, it's just about simply driving the system from some initial configuration in little L2 into some final configuration in little L2. Of course, I didn't say, but I am also assuming that the operator B is bounded and so on, right? Do you think that there is any risk that saying that the rank is infinity doesn't capture what's going on? What is the risk? Right? So this is not enough. This here is not enough. Why? Because you could have the rank to be infinity, but only have, say, for instance, the even components of the system or the odd components of the system, right? So it could be that out of your, you know, your infinite dimensional, say, space, you can only control the red components, right? But not the others, right? Not the yellow ones, right? In such a case, you will still control an infinite dimensional subsystem. The rank will be infinity, right? But you will still be missing all the even components. Again, you will be missing a complete infinite dimensional projection, right? That will not be controllable by the system. You can, of course, build systems that way. Just using playing with this, right, is basically the same system I wrote, right, the other day, where you have this and then this, right? And then I said, well, of course, the X2 is controllable because the U is acting on X2, but the X1 is non-controllable. You can reproduce this infinitely many times if you want, by making the numbers here, right? Making the numbers here to be small and small and smaller, so to be little L2. But you reproduce this, say, a structure of one component controllable and the other one not being controllable. And then you see that in the infinite rank condition, you don't see the controllability of the system. It cannot be written that way. Okay. So now the question is how we address this problem. And this problem is relevant because all systems in continuum mechanics are infinite dimensional. So our first trial to handle this with the classical Kalman rank ideas failed. Thank you for your attention. So let me then go back to this issue. So we have seen that, can you actually see me? I don't see myself.
It's working.
It's working, okay, yeah, okay, thank you. So as we said, the first attempt of moving naively from the finite dimensional theory to the infinite dimensional theory fails. Because in particular, of course, in an infinite dimensional space, you can have many infinite dimensional subspaces, and then saying that the rank condition is generalized to this, at most, it will mean that you can control some infinite dimensional projections, but you will not get full information on the system, right? Then, as I said the other day, there are two very interesting papers. One is by David Russell, both of them published in Siam Review in 1978, and the other one by Jean-Louis Lyons in the same journal in 1988. They revisit this topic and they set up somehow the foundations of what, you know, has been a very, very rich, you know, literature in this area, right? The question is, after all, how you reformulate the problem and reinterpret the problem in a way that you can really develop tools that allow you to address and fully understand this issue of controllability for infinite dimensional systems, okay? And this is, you know, in the context of transport, right? So the example number one will be the transport equation, right? And in that setting, we have considered this system, right? And what we have, you know, discussed previously today, and is very related to the discussions we have on the control of neural differential equations, is the control on the velocity field, right? Okay, very good. So this is an interesting observation that says, be careful, because when you move from, even in the context of linear transport equations, when you try to use the paradigm of transport as being simply understood in terms of characteristics, things get very tricky, right? Because you see, in the linear finite dimensional context, right? This is a linear control problem, right? But if I write this equation down as a transport equation, right? What I see now is that, right? The control is entering now as a coefficient in the equation, right? So then this becomes a linear control problem in the ODE setting, becomes a nonlinear control problem, right? Why? Because you see, yes, so the equation F is linear once you give me the U. But as we were discussing yesterday, the dependence, right? The dependence, the mapping from U to F is non-linear, right? So this is not a linear control problem, although the equation is linear on F. Why? Because the control, right, is entering here as a coefficient multiplying the state, right? You could check it yourself. You could take U1 and then U2, F1 and F2 corresponding to the control U1 and U2. And of course, when you add these two equations, you will not be able to really, get anything clean out of it, right? So the observation is simply that this is definitely not the case, right? This is unfortunately not the case. So you see that if you think in this other possible connection, one possible connection was take the linear system as is written here and take the dimension and go to infinity. We said, well, this is not so clear because rank infinity is not a precise notion. Another possibility will be to say, okay, let me, consider the controllability of this finite dimensional system and let us interpret it as the control of a transport equation. Well, of course, if you do this, you will be only dealing with this transport equation. You will not be dealing with other models like a Schrodinger equation or the heat equation, right? But furthermore, you will be considering problems in which, the control is centering on the coefficients of the equation, right? This is, of course, makes sense, but is not really the first prototypical model one could consider. It would be much more natural to take, for instance, a drum, right? So take a membrane, right? Occupying the domain omega in R2, right? And consider the wave equation for the vibration of that membrane, right? Okay. This is one of the simplest and most important equations, right? So this is the wave equation in which we are considering the vibrations of this membrane, right? Very good. We know that the solutions of this system can be expanded in Fourier series. We know also that the energy of the system is conservative. This is just the harmonic oscillator put in an infinite dimensional context. If I will multiply the equation by yt, right, here, if I will multiply the equation by yt and integrate over omega, I will have the energy conservation identity, which is ET is just half of the integral of the potential energy plus half of the integral of the kinetic energy, right? And this energy has a zero derivative, meaning that the energy is conserved, right? In particular, this means that, whenever you give me initial data on this system, which have a given level of energy, and in particular are non-zero, the solution will never be zero, right? This is a permanent vibration, an endless permanent vibration, right? In an infinite dimensional space, right? So in other words, if we will draw the energy space here like an infinite dimensional Hilbert space, like little L2, what we have here is a sphere, right, of a given radius, which is the energy of the initial data, and then the trajectory is simply an endless, rotation on the surface of this sphere without never losing energy, right? Well, of course, this is not completely realistic. Every mechanical system develops some kind of dissipation, right? So even ourselves, you know, you can give lectures and give lectures and give lectures, but of course, at a given time, you start being tired, right? There is some dissipation of energy. There is friction with the exterior medium, right? Okay. So you could, for instance, consider maybe more realistic model, right? Is the wave equation with damping, right? I keep the zero boundary conditions just to fix ideas, right? I could consider other, right, boundary conditions. The fixed boundary conditions are corresponding to the case of a drum, right, which is fixed on the boundary, and I'm just, you know, the vibration is ongoing inside, or the chord of the guitar that is fixed on the boundary and then is vibrating in the interior, right? This is just a very simple model in mechanics. Zero direct boundary conditions is a very natural prototype to consider, right? So now this velocity term I am introducing here is a damping. Why is this a damping? Because if you write the equation down in this way, and this is the way we like it, you know, the mechanical interpretation, if you go back to the books in continuum mechanics, what you see is that the mechanical interpretation of this wave equation with right-hand side minus yt is a volume force, and therefore this is a volume force or an interior force, right, which is acting everywhere inside the domain, so that at every point is applying a force that is oriented in the direction of the velocity, right, but always with opposite sign, so that when the membrane is trying to go up, you are pushing down. And when the membrane is trying to go down, then you are pushing up. So this is exactly similar to, you know, the harmonic oscillator problem that, you know, Maxwell was considering. Of course, we could also put some damping coefficient here, right? I could put a constant K here, the same way we did put a constant K here. And we recall what Maxwell said, be careful, there can be overdamping. In particular, it's not because K is larger than the energy is dissipated more effectively. You know, there is a threshold on which this intuition that, you know, the decay of the energy improves when K increases is saturated, and then you go down, right? Okay, keep in mind. Very good. Anyhow, what about this system? So there is damping, and therefore, if I multiply, let me, in order to fix the discussion, let me take K to be 0, right? Sorry, to be 1. I can consider also the more general case later if you wish, but this will simply change the computations a little bit and making them more lengthy, and nothing will change qualitatively. So let me take the damping coefficient to be 1. And then I ask you, okay, so we agreed that this should lead to some kind of dissipation of energy, but how can I see it? Well, you see it in the same way. You multiply the equation by yt, you integrate in omega, the energy of the system is defined in the same way, it's just the superposition, right, of the potential energy, right? So this is the potential energy, and this is the kinetic energy, and this is the total energy. And then when you compute the time derivative of E, what you get is minus the integral over omega of yt squared. Right? So clearly, this is negative, and then ET decreases as time increases, right? So this is a dissipative system, and the fact that it's a dissipative system is simply observed on the fact that the energy is going down, right? But then the question that arises naturally, and this was before getting into sophisticated discussions about the control of infinite dimensional systems, this was done much before, right? In particular by LaSalle. It was this idea that, okay, to which extent the theory of Lyapunov systems, you know, the existence of Lyapunov functions, for instance, on the gradient systems, in which you can apply the invariance principle, saying that, you know, the energy goes down and down and down until it's minimized. So can I use this in this context? So is it true in particular that the energy goes to zero as t goes to infinity? And maybe even better, is it true that I have some kind of decay property which is exponential, right? So these are the kind of questions that people looked at, you know, starting in the 60s and so on, right? How can we handle this? Well, this doesn't look very difficult, right? Because we have the energy, right? The energy here, right? We have the energy. Sorry, it's not very visible if I do this, right? Okay. So we have the energy. And we have the dissipation of energy. Right? Of course, I will be delighted if I could, you know, if we had, right? If we had something like the derivative of the energy to be less than minus alpha E of t, I will be very, very happy, because then by Gromval inequality, I will simply have that the energy ET will be smaller than E0 times exponential minus alpha t. It's just integrating this inequality that you get this, right? As you know, the proof of that is very elementary. I simply rewrite the fact that the derivative of the energy is less than minus alpha E. I can rewrite it as the derivative of the energy plus alpha E being negative. If I multiply here by exponential alpha t, I observe that this means that the derivative of exponential alpha t et is negative. This means that exponential alpha t et is less than the value at t equals 0, but at t equals 0, exponential alpha 0 is 1, and this is E0. And this implies that ET is less than exponential minus alpha t is 0, right? This is the proof. It's very simple. But do I have this? Well, what I have here in the dissipation, I have just the kinetic part. While in here, right, if I will expand this, I will have the kinetic part and the potential part, right? And I don't have this, right? When I look to the dissipation law I have, right, if, you know, because of the way the damping term was designed to be a velocity damping, so this is a velocity damping, because the force that is compensating the dynamics is proportional to the velocity. This velocity damping is damping the kinetic energy, but is not in principle damping the potential energy. So, you know, it could, you know, I wonder then whether, you know, the danger, right, will be if I was, for instance, in a situation where I have an harmonic oscillator where one component is, undamped. One component here, X, is undamped, and this one is damped. If I take this harmonic oscillator, what I will see is that the X component is constant amplitude, does not decay, it oscillates, it's just a combination of sinus t and cosine t, and the yt decays. But as a whole, of course, the system does not decay. You see that this is the same arguments as we used to say that if the A-B condition fail, the system is not controllable because there is part of the system that is not controlled at all. So there is a projection of the state that cannot be controlled. The same here, right? So this is the danger. But does this danger occur in here or not? Is this true that, in such an equation, the fact that I am in principle only damping the velocity, is it true that it's only damping the velocity, or it has some, effect also on the potential energy? So the question, which is very important from a mechanical perspective, is the question is, does the velocity damping on the wave equation have an impact on the decay of the potential energy as well? Well, this is not so obvious, right? So what people thought in the 70s, there were works by, in particular, so this was in the 70s, right? There was works by Constantin Dafermos, and then Alain Aron in Paris, who was my PhD advisor, and so on. People thought, well, maybe we should elaborate this question a little bit more, right? So then the approach that people derived was the following. The approach was find a perturbation of the energy so some E epsilon, right, equivalent to the energy in some sense, such that you could actually see that when you compute the derivative of ET, not only you get the dissipation of the, kinetic component of the energy, but also you make emerge the fact that this velocity damping has an impact on the potential energy, right? So this means make it visible that the velocity damping has also an impact on the potential energy. Okay. And if you think on this, you realize that this is not that far from what we are doing in the Kalman run condition, right? In the Kalman run condition, we say, oh, in principle, right? In principle, when I look to the system like this, apparently, when I use control U, the control U is filtered through B, and B is not acting on the whole state X. It's just acting on some of the components of X, just on the rank of B. But what we understood through the rank condition is that this is correct. At a given time instant, the U is only acting on the rank of B. But on the other hand, the system X is evolving. It's evolving because of the dynamic generated by A. So the system X is also rotating. Therefore, maybe the fact that you are acting always in the same direction of the B, which will be insufficient in case, you know, the system was always evolving, you know, parallel to the action of the control. The fact that the system is rotating maybe means that if you act on one component, then all the others will also be affected as well. Right? This is like, you know, you are controlling a building, it's empty in the morning, you open it in the morning at 6 a.m., and then people start getting in. If you are in the door of the building, then you can count how many people are getting in. You are static, you are the B is not moving, but people are incoming. Therefore, the flow is bringing you the information to the sensor, the same as, you know, when the flight attendants are counting how many people are getting into the plane, right? To really check whether, you know, the 132 tickets that were sold, all people show up to travel, right? And they know then they can close the door and depart, right? Without waiting anyone else. So you see that in the linear, already in the linear finite dimensional control theory, we have enjoyed of the fact that the system is evolving so that the action of a given control is able to, right, control the dynamics of the system. And this is actually what happens in the harmonic oscillator, right? So this is successfully achieved for the harmonic oscillator, right? Because what is the harmonic oscillator doing, right? If you draw the trajectories on the phase space, we know that the harmonic oscillator, the energy is conserved, so the trajectories are trapped on a level set, but they are rotating, right? So we are in principle only dissipating on the vertical component. We are pushing down only with the velocity x prime. But we are doing it all the time. Because the system is rotating, eventually, you know, the system will be under the action, successful action of the control all the time. And even, you know, the part of the energy that was sitting here, and that at time t equals 0 was not dissipated because the velocity here, x prime, is equal to 0. So the action of the vertical force has no impact. This particle here eventually will rotate, right, and come to a place where the damping will be effective. So that's the idea of the Kalman rank condition. And this is really, you know, coded in this full rank condition. B, AB, AN minus 1, B is equal to 0, is equal to N. As we said, if it is not N, if it is N minus 1, it means that, oh, you were quite good, but you miss one component. Then you will not dissipate all the system. And this is what we did, right, when we consider, right, the case where A, right, is antisymmetric, right? And we have seen that such a damping term, right, is successful on the control of the system. If you do this, you realize that indeed, in this case, the damping on the velocity is sufficient. Okay, fine, that's very clear. But then we go back to the question. The question that was formulated was, okay, if we want to move to the theory of partial differential equations, and be able to handle, for instance, wave equations, Maxwell equations, Schrodinger equations, which are infinite dimensional systems that are conservative, it would be great to have a means to build, you know, perturbations of the energy, Lyapunov functions, if you want to, so that not only you have the dissipation that is completely obvious in the wave equation through the term kinetic energy, but you make also visible, right, the emergence of the potential energy, right? And this is where, you know, people realize that a very interesting way of doing this in the context of the wave equation, for instance, is to do the following. They said, okay, let me take the energy and let me add this little, say, extra term, right? With epsilon positive and small, right? You will understand why. So the first thing to do is to observe that E epsilon is completely equivalent to E. What does it mean? It means that half of E is going to be less than half of than E epsilon, and this will be, for instance, less than 2E, or if you wish to say 3/2E, right? What do I need in order to do this? Well, the only thing I need in order to do this, because I am adding this extra small perturbation to the original energy, the only thing I need in order to guarantee this is that the absolute value of this, right, which is less than, you know, the absolute value of epsilon, and then the integral of the absolute value of y and the absolute value of yt, right? I need simply to guarantee that this is smaller than 1/2 times the energy. Well, because I have a epsilon here, this will be true as soon as I am able to show that the integral over omega of absolute value of y times absolute value of yt is less than the energy, right? Is this true? Well, I apply Cauchy-Schwarz, right? Sorry. And I can, for instance, right, I could improve the choice of the constants, but just to make it more visual here, I could do this, right? And I say, oh, this is the kinetic energy, which is part of the energy. Fine. But what about this? This is the integral of y squared in omega. And this is not part of the energy. Remind that the energy was kinetic energy plus potential energy, right? Kinetic energy plus potential energy. And the potential energy involves the gradient of y, but not y. So how can I prove, right? How can I prove, in this case, that the term here is also bounded by c times the energy? How can I do it? Do you have any guess of how could I do that? Is there any other inequality you know in functional analysis that could help me on doing this? I could use the Poincare inequality, right? And the Poincare inequality says that when omega is bounded, there is indeed a constant c, so that the integral over omega of y squared is less than the integral omega of gradient y squared for all y in h10 omega. So that's it. So the first goal is achieved. The first goal is that when you add to the traditional energy, the natural energy of the system, you add this small correction term, right? Then the new energy is completely equivalent to E, in the sense that you can guarantee this inequality, provided the epsilon is small enough. And because this is true, right, then you can guarantee that the exponential decay on T of ET is completely equivalent to the exponential decay of E epsilon T on T. Both of them are completely equivalent. So if I prove the exponential decay of E epsilon, I am done. Okay? Now, how do I succeed to do this? We say, okay, let me try. E epsilon is E plus epsilon, the integral over omega YYT dx. So I take the derivative of E epsilon. This is the derivative of E plus epsilon, the time derivative of the integral of YYT. The derivative of E is minus the integral over omega of YT squared plus epsilon. Now, when I take the derivative in time of YYT, the first term will be YT, derivative of Y, so it will give me YT squared, right? And the second one will be the integral of omega of YYTT. But YTT, so this remains the same, this remains the same. YTT is equal to the Laplacian Y minus YT, right? So then I will get the first term, the second term. Now here, you see that the integral of Y, Laplacian Y, integrating by parts will give me minus epsilon, the integral over omega of gradient Y squared, right? And then here I will get another term, YT. And this is the magic, right? The magic is that thanks to the introduction of this small correction on the energy E, which doesn't change anything in the sense that E epsilon and E are totally equivalent. When you introduce this corrector term, you have succeeded on making, you know, this potential energy with a minus sign, the dissipation of the potential energy, make it appear in the picture, right? Okay. And then when you do this, then eventually you will have that the time derivative of E epsilon, it will be minus 1 minus epsilon, right? Because here I had minus YT squared. This is the damping introduced by the damping term. But I have an epsilon that I am losing because I am adding a little bit of kinetic energy through the derivative of this term, right? I still have 1 minus epsilon that, of course, will remain negative when epsilon is less than 1 times the kinetic energy. I have here minus epsilon, the potential energy, right? If these were the only two terms, this will be great because I could simply say that this is less than minus 2 times the minimum of epsilon 1 minus epsilon times the energy, right? Or something like this. That would be great. This is really what I need. But unfortunately, there is a small reminder term, right? And then if you ask me, what can I do with this? I say, well, I really don't know because this is really no sign, right? The integral of YYT, I really don't know what it is, right? So what can I do? What can I do with this? So I could, for instance, take epsilon YYT and using Cauchy-Schwarz, right? And classical inequalities, I could, for instance, show that, okay, if I take here, I could make, for instance, this less than 1 over 2 the integral of YT squared plus now epsilon squared over 2 the integral of Y squared. This is just Cauchy-Schwarz again. And this will be less than 1 over 2 integral over omega of YT squared. And then I could apply, you know, Poincare inequality with the corresponding constant C, and this will be C epsilon squared over 2. When I put all these together, what I will get is that the time derivative of E epsilon will be less than 1 minus epsilon. Now I am paying an extra 1/2, so I will have here minus 1 over 2. the integral over omega of yt squared, right? And then here I will have, rather than having minus epsilon, I will now pay the price C epsilon squared divided by 2, the integral of gradient y squared, right? Is this okay or not? Can I make this to be positive? Yes, of course I can, because this is 1 over 2 minus epsilon. If epsilon is less than 1, 2, this is positive. And what about this one? Is this positive or not? Well, again, if epsilon is small enough, the quadratic term is negligible in front of epsilon. So for epsilon small, right? If epsilon is small enough, but certainly positive, I can make this to be less than, for instance, 1/4 of the integral of yt squared minus epsilon over 2, the integral of gradient y squared, right? And this will be certainly less than minus epsilon times the energy, okay? And this implies immediately, because this is less than minus epsilon 2 times E epsilon t, this immediately implies the exponential decay of E epsilon and therefore of E of t. Okay, so these were the computations that were done in the 70s, right? So people said, oh, damping is fine, right? If I am damping the wave equation, right, I am able to show that, you know, that the wave equation, right, so I think it's here. Oh, sorry. Now, I will be able to show that this wave equation, right, exponentially decays when I add this damping term. Very good. And the game to play, as I have shown, is to, you know, perturb the energy, right, as in here, right, perturb the energy by adding some delay here. Okay, here it goes. Perturb the energy by adding this cross term, right? So this is very much related to the theory of hypoellipticity developed by Hormander, later further developed by De Villet and Villani for, say, kinetic models in the context of the decay of Fokker-Planck equations and related kinetic models, right? So, and you can apply this to many, many different, say, models, right? After all, what we are using here is something that somehow is implicit already in the Kalman-Rank condition, right? So, as I said, you know, this idea of augmenting the energy to make it more visible, the dissipative effects on the various components of the system can be extended to many other models, right? Actually, if you go back to the finite dimensional system again, which is always the laboratory we like to think on in order to better understand complex concepts, because then they simply become linear algebra issues, which can be also tricky, of course, but you remove all the burden of the dynamics and the infinite dimensional dynamics, in particular of partial differential equations. This is already implicit in the Kalman-Rank condition, because we say that AB is controllable, right? Whenever the rank of B, AB, AN minus 1B is equal to N. Okay? And we use that already when we establish the duality between controllability and observability, according to the old idea of Norbert Wiener that, you know, communication and control sensors and actuators have to cooperate to really develop, you know, the new technologies and new systems of cybernetics, robotics, and so on, machine learning. We know that the rank of this matrix being full is equivalent to the kernel of the adjoint, right? To be void. So then I ask you the following question. Do you agree then that whenever this condition is fulfilled, which means that the system is controllable or AB fulfill the Kalman rank condition, do you agree with me that if I take the Euclidean norm, right, is equivalent to this other norm of a vector that the norm of B star X squared plus the norm of B star A star X squared plus A star N minus 1 B X star squared? What are we doing here? So X is a vector in Rn. And the dimension of this vector n will be huge when I am dealing with a large dimensional system, for instance, a social network, right? Millions of users, right? So n will be millions of them. B star is a matrix m times n. So in here, in B star X, I'm just see an n-dimensional projection of X, right? So out of this huge vector X, for which I wanted to compute the whole norm, I have simply taken here a m-dimensional projection, right? B star X. But here, I have taken again a m-dimensional projection through B star, but not of X, but a rotation of X by the matrix A star. And here in the next term, I take again an m-dimensional projection, but of A star square X, so another rotation of X. So my claim is that these two norms are equivalent. The Euclidean norm, I mean, it's not a norm adapted to the system. I mean, it's the Euclidean space. I put a canonical norm simply because I, as a human, I understand that there is a vertical direction because I live standing, right? So we are driven by gravity. We are vertical, say, we have a vertical body, right? So there is a vertical variable. This is clear. And now when I look around me, I see a plane with two canonical directions. Fine. This is my understanding of the Euclidean space. But this has nothing to do with the system AB. Yet, the point is that whenever the system is controllable, there is a norm which is completely equivalent to the canonical norm in the Euclidean space, which is very much adapted to the system, right? And this norm is given by this. Why is this true? Well, because in the Euclidean space, all norms are equivalent. And this definitely, which is just the square, I mean, if I will take here the square root of this, the square root of this, of course, this is a semi-norm. And my only concern to show that this is really a norm is that whenever this quantity is equal to 0, X is equal to 0. But why, when this quantity is equal to 0, x is equal to 0. Why is that? Well, because precisely I have the dual version of the Kalman rank condition, which says that there is no vector on the kernel of this big operator other than x equals 0. So whenever you tell me that this is equal to 0, although this is only an m-dimensional, very narrow projection, but you tell me the same, not only for x, but for all the rotations that I get applying a star squared, a star cubed, up to a star n minus 1. Whenever these all projections are equal to 0, then x is equal to 0. So this is an equivalent norm. And you see that I don't lose this equivalence if I allow myself to put here a number epsilon 0, a number epsilon 1, a number epsilon n. So you take all these epsilons to be positive, you are building a norm that is completely equivalent, right, to the Euclidean norm. And this norm now, this norm is really adapted to the system, right? So when you look to what we did here, right, what we did here for the wave equation, when we moved from, say, the energy E into the energy E epsilon plus epsilon, the integral y t dx, is nothing but, you know, this term here, right, is nothing, sorry, we move from E into E epsilon, which is E plus this term. This term here, which is measuring the crossing between y and yt, right, is precisely this term here. It's just, you know, not only the obvious dissipation you have on the system, the yt component, but is the b star applied to a star b. This crossing here is the one that is coming out of this, say, second term in the norm of Kalman, right? And this is precisely what the hypocoercivity does, right? So this is related to the classical concept of hypocoercivity, right? Hypocoercivity that was introduced by De Villet and Villani. You know that Cedric Villani got the Fields Medal, right? Maybe, I don't know, in the 90s, right? But it's also very much related to the context of the concept of hypoellipticity that was introduced by Hormander, right? Right? What is hypoellipticity? Well, in principle, the PDEs, right? So the PDEs, when we take the classical textbook, they tell us there are the elliptic, there are the parabolic, and there are the hyperbolic, right? I mean, the elliptic, of course, is minus Laplacian in x. The parabolic is the here operator, dt minus Laplacian on x. And the hyperbolic, there is the, right, second derivative in time minus the Laplacian in x. But there is a celebrated equation that was analyzed by Kolmogorov, right? That is, you know, the Fokker-Planck equation, actually. And it can be written in that way, right? So it's an equation that looks like this, right? So when you look to this equation, you see, oh, this is kind of a mix, right? So, right? So this is the heat equation. This is parabolic, right? But then when you look to this other term, right? This is like a transport equation. And this is hyperbolic, right? And then Kolmogorov was analyzing this equation, and he found something surprising. Why? Because what do the parabolic equations do? The parabolic equations, they take a Dirac delta, and out of a Dirac delta, you develop a Gaussian. This is the Gauss fundamental solution of the heat equation, 4 pi t minus 1 over 2 exponential minus x squared over 4t. This is fundamental equation of the heat equation, and this shows, that, the parabolic equation is extremely regularizing, is diffusing, right? Is taking a Dirac delta, the mass that is concentrated on a single point will diffuse it all along a space, regularizing it, because here you have a measure which is not even an L1 function. I mean, this is a singular measure, an atomic measure, and is mapped into a function that is analytic for T positive. Cannot be better as a regularizing process, right? This is parabolic. But as we have seen for hyperbolic equations, right? Transport, when you look to transport phenomena, in particular, when the velocity of transport v is a constant, then you know that the solution, as we have shown before, is just transported along characteristics. This is just, constant transport. There is a wind, right? And this wind is transporting the initial profile into somewhere else, right? Without any deformation, because v is a constant. All characteristics travel in parallel with the same velocity. And here, this is a regularizing effect. But here there is no regularizing effect, simply because the profiles of the solution remain the same. If you will give me here, rather than giving me this smooth profile, you give me a jump function, a characteristic function. The characteristic function is transported as characteristic function. If you give me a Dirac delta, the Dirac delta is transported somewhere else, but is transported as a Dirac delta. So then when Kolmogorov looked to this model, this Kolmogorov or Fokker-Planck equation, he said, well, this is kind of a mix of parabolic in X, but hyperbolic transport in Y, right? In particular, right, I could expect that, the solutions, we could expect right, that the solutions of the Kolmogorov equation will be smooth in one variable, right? But with a jump, right? A jump like a cliff, when you are walking on the mountains and you get to the end, to the edge, and you see, the sea, or in front of you, the ocean, right? You are, on an edge. We could have expected something like this, right? Something that is smooth in the variable X because of the parabolic term in the equation, but singular on the variable Y because, there is no smoothing effect on the Y equation. But when Kolmogorov computed the fundamental solution, right, it is completely explicit. He discovered something fundamental, is that the fundamental solution is a Gaussian in X, but also on Y, right? And he said, oh, that's amazing, right? This is a, it's a equation which is Gaussian in X, fine, because you see, there is diffusion in X, but it's also Gaussian on Y. And why is that? Why is that? It's because you see in here, right? So this will not be true, right? So our intuition, this very, very basic intuition, this intuition is okay if I consider this model. In this case, this intuition is correct. This parabolic in X, regularizing in X, transport on Y, not regularization at all. I will get solutions which are like cliffs. You know, I will get a smoothing on the X variable, but on the Y variable, the rough singularities like of a characteristic function, a cliff here, will remain. This will never be regularized. This intuition is correct in this system, but the intuition is not correct for this system. Here, although for every X, this is a transport equation on Y, you see that there is motion on X and T. The system, you know, this is a mechanical system, it's evolving in X and T. So it's not totally legitimate that I think on this system as X being frozen, because there is motion in X as well. So the key issue, right, is that, you know, the key fact is that in the model, the two differential operators D2xf, sorry, or D2x and dy, so two derivatives in X and one derivative in Y commute. Right? You agree with me that in the context of distributional theory, you don't really make the distinction, right? Two derivatives in X, one derivative of Y of f is the same as one derivative of f and two derivatives of f in, you know, the space of distributions. But the commutation does not hold when you consider now this operator and this operator. I give you 2 minutes. Please tell me what is the gap you find between this operator and this operator. Are they the same or there is a gap? And in case there is a gap, please write down what the remainder term is. I will be back in 2 minutes. So could you please tell me whether you got some gap term? Is there some error term? Oh, is 2 phi x phi y. Oh, I see. Phi, yeah, I see. Delta. I see. Thank you, Ma. Let me see. Is this true or not? So let me compute 2x derivatives of x dy. So I have to take first one derivative and then the other. When I take the first derivative, I get the first derivative in x of x gives me 1, so I get dy, and then I have x, and then the second derivative in dxy. And now I take a second derivative, and then, of course, here, no problem, second derivative in xy. And then when I take the x derivative of x, I get another term like this, so 2. But then I get also the term x d3, d2x dy. And when I do the other, if I do the other, what I just get is simply this. I get x dy, the second derivative in x. So the gap is here, right? Which is as, yeah, this is precisely what Ma was writing, 2 times the derivative in x times the derivative in y, right? Thank you, Ma. Okay, so there is no commutativity. right? And the fact that there is no commutativity makes that you win. And this is what Kolmogorov called, or maybe the terminology is due to it could be that the terminology is due to Hormander, hypoellipticity, right? Right? Hypoellipticity, the equations are hypoelliptic. You don't need to be parabolic. It could be kind of a mix of parabolic plus hyperbolic with this interaction term due to the brackets, to the lack of commutativity. The Lie bracket, after all, when I am saying here that, there is no commutativity, what I'm computing here is the Lie bracket between one operator and the other, right? And showing that this is some non-trivial operator, right? So hypoelliptic equations are those that, without being parabolic, are so that the fundamental solution, which is the parting out of a Dirac delta, is regularized, right, in all directions of space. Okay, that's the concept of hypoellipticity. And then there was the seminal paper in the 60s by Hormander, who really characterized this through a condition that is really equivalent to the Kalman-Rank condition. And the reason is precisely the one we have described here. In the context of finite-dimensional systems, right? This is simply this idea of realizing that actually through the Kalman-Rank condition, we are being told, right? Actually, we should have observed that sooner, right? As soon as I said that the Kalman-Rank condition can be written as the void kernel, right? The trivial kernel for the adjoint, I should have realized that the way to interpret this should have been that this norm is equivalent to the Euclidean norm in Rn, meaning that I am enjoying of the fact that even though I am applying only a very narrow B star projection, the system is rotating under the action of A, right? And this is precisely what this is telling me, right? This is telling me that, listen, you know, what is this telling me? This is telling me, listen, Enrique, apparently in the whole Kolmogorov equation, the diffusion is only acting on the X variable. You have only two space derivatives on the X variable, right? Yes, but then because the system is evolving under the action of the first order term, right? The action of this second order X derivative on the flow generated by the other equation, right? Okay, the action of the first diffusion on the evolution of the semigroup generated by the second equation, right, is having the impact of the second derivative in xy, which is just the derivative in the oblique direction. And then because we are in xy, I don't need, in order to gain the regularity of the heat equation, I don't need the Laplacian to be in x plus in y. It is sufficient for me to have it in x and then in an oblique direction. I have diffusion in all directions, and this is what generates the hypoellipticity or the hypocoercivity of the Kolmogorov equation. So you see that we have found a different connection of the theory of control, dissipative systems, decay of the energy, this very elementary computation on the wave equation that looks like as, you know, a curiosity, right? Oh, why don't you add the integral of YYT, the link with the Kalman norm, the fact, you know, the dual interpretation of Kalman, and the fact that this is intimately related to, you know, the theory of hypocoercivity and hypoellipticity. And there is just one last remark I would like to do, maybe it's the last one today, is splitting, right? Splitting, right? Which is very much related also to domain. decomposition, right? Okay, so what is this about? This is somehow the opposite to what happens here, right? It's somehow related, but the point of view is different. So you see here, what was the point of view of Kolmogorov? Right? Kolmogorov was looking to this model, right? Then one operator, another operator, and the combined effect leads to something surprising. Surprising in the sense that, you know, the lack of commutativity due to the presence of X makes, you know, that, you know, this profile, the profile of the solution is not the one I expected naively, like a smooth in X and irregular in Y. There is also a regularization effect on the Y variable. And this was due to this interaction, okay? Good. But when you adopt a more computational perspective, so this comes more from a computational perspective that was not the one that was pursued at that time by Kolmogorov and Hormander when working on this. They did so many things that certainly they did also other developments from a more computationally oriented perspective, but not at that point, right? Then, you know, in mechanics, we build basic models, and then when we are facing more and more complex phenomena, we have to make these models to become more and more complex. But then, of course, this has you know, an impact, right? So the tools we need to use for control, machine learning, computations, numerics, they become more complicated, and the understanding of the dynamics becomes also much more sophisticated. And then from a computational perspective, the issue that arises is, okay, so even in the matrix case, right? If you give me this system, what is the solution of this system? And then I will tell you, well, that's very easy, right? The solution of that system is going to be exponential of A1 plus A2 times T times X0. This is the solution, no problem, right? And this in, you know, in the finite-dimensional context, there is no ambiguity. A1 is a matrix, A2 is another matrix, A1 plus A2 is a matrix, and I know the exponential is well defined out of a power series expansion. No problem. Yes, but when you are in a more mechanical context, it could be a viscoelastic model. It could be a fluid structure interaction system. It could be the fluid, could be the air, the structure could be the airplane or the boat. It could be the human cardiovascular system. The fluid is the blood, and the structure are the, you know, the walls of the arteries that are elastic. Right? So there are many systems in which A1 and A2 have a very different nature. And my dream, you know, in the impossible dream, right? So the impossible dream will be something like this, will be to say that this is exponential A1t, exponential A2t, X0, right? Because then I will say, listen, if I want to solve this system, it's very simple, because then I need only to solve first this equation, plug the output of this equation into the second one, and then solve the second equation, right? And maybe if I am lucky, I even have the reverse, right? So I can do it in the reverse order. Now, my question is this true? Is it true that the exponential of the sum of two matrices is equal to the product of the exponentials? Yes or no? Let's vote. If they commute, good. So Ma says that this is only, right? This is only if A commutes. So if the commutator of A1 and AB is equal to 0, meaning A1, A2 minus A2, A1 is equal to 0. Oh, this seems to be related to Kolmogorov and Formander, right? Hypoellipticity and hypocoercivity. So this is true only if they commute. So what does it mean? What is the interpretation we have to do out of this? The interpretation is the following. In a system like this, in a system like this, when you have two independent effects driving the dynamics, right? When the two operators commute, nothing new happens. What you get is really, the output of the action of one and then the other, right? As our simplest intuition says. But the fact that when A1 and A2 don't commute, this is not true. The fact that, the full dynamics is just, the consecutive application of one and the other tells you something very interesting. Could be dangerous or could be helpful. It tells you, be careful, because whenever you are solving this system, which is a joint multi-physics research system in which you are taking into account two different physics or two different phenomena like convection diffusion, transport diffusion, elasticity, viscosity, viscoelasticity, memory, whatever, right? Multiple scales, nano, micro, macro. Whenever you are piling up different, say, operators in your dynamics because you want to make your model richer and richer and richer, yeah, you are making it richer, but please don't think on it as being simply, a cake in which you are putting one layer and another and another and another. These layers start to melt, and then you get composite effects. You get mixed effects, cross effects. And this is what the theorem says. In case, or this computation says, in case there is no commutativity, you get new phenomena. And why is that? Well, it's very simple, because you see, it is sufficient to observe that if I compute A1 exponential of A1 plus A2, then if I do the power series expansion, the first term is 1, the second term, or the identity, the second term is A1 plus A2, the third term is going to be A1 plus A2 squared divided by 2, and then there are others, right? And then when I expand this term, A1 plus A2 multiplied by A1 plus A2, I have A1 squared plus A2 squared. And be careful here, because if A1 and A2 don't commute, this gives me A1, A2, but also A2, A1. But when you do, for instance, exponential A1 times exponential A2, I'm doing just the, the product of the expansion of A1, identity, and A2, the square, and so on. And when you expand this, you have identity times identity, identity. A1 times identity and identity times A1, A2, I get A1 plus A2. And then I also get as quadratic terms, right? A1 square times identity divided by 2. I also get A2 square identity, so I get also A2 square divided by 2. And I get also A1, A2, right? But, I get A1, A2. But what happens then? But I never get A2, A1, you see? This is why the two dynamics, don't really coincide. So these dynamics is richer this dynamics is richer than the dynamics generated by A1 and then A2. There is an interplay that leads to different phenomena. Okay? This is something, as I mentioned before, that it was observed in domain decomposition. I think this was in the late in the late 19th century. You know, for instance, if you try to solve the Laplacian, then on the square is very simple, right? In a square domain of R2 is very simple. You can actually compute the eigenvalues and the eigenvectors of the Laplacian on the square, right? It's sine kx, sine my, right? And the corresponding eigenvalue will be k squared plus m squared. And this is true in the domain 0 pi, right? So in the square omega, 0 pi squared. Now, if you give me, right, the Laplacian on the disk, right, then I can do it in polar coordinates, right? So then it's a bit more tricky, but I know the eigenfunctions can be written, right, in polar coordinates like this, right? So the angle dependence and then the radial dependence. So there is separation of variables in here, right? There is separation of variables in here and separation of variables in here, except that the variables, of course, in this case, right, the variables are simply the Cartesian x and y coordinates, while in here, right, this is the, you know, the radial coordinates, right? More thinking in, you know, in this onion ring structure, concentric rings, right? Good. And then people thought you can find this history described already in the book of Curran-Hilbert, where they have a very nice introduction to domain decomposition. There was someone who said, well, and why don't I try to compute, right? My drawing is not perfect, no means. Why don't I try to compute the eigenfunctions of the Laplacian in this domain? Right, so this domain you see is just the intersection or the union, sorry, of this red rectangle and this green circle, right? So this should be really a circle. This should be really a circle. Okay, very good. Okay, now how can I do it? And then you start thinking, so can I compute? So this is, if this is the domain omega, the domain omega is really the union of these two pieces. You are putting together, you know, two three-dimensional, or in this case, two-dimensional domains to build a more complex two-dimensional domain. And then, you know, people said, can I compute the eigenfunctions of the Laplacian in this domain? And then people soon realized that that was tricky, right? So, you know, as I said, this is simply the union of two media, right? The disk and the rectangle, on which you also have some common interface, which is given by, you know, this kind of rectangle, right? But with a curved side. And then people started to try to compute the eigenfunctions of the Laplacian, and they soon realized that they were not able to do it. You can try yourself. The difficulty is that when you are in this domain, you like to use radial coordinates. But when you are in this domain, you like to use Cartesian coordinates. And there is not a single coordinate frame in which you could compute things in both sides. So they failed. And this is how they derived the domain decomposition technique, which is probably one of the most, say, powerful tools in computational mechanics, in applied mathematics, in scientific computing. It was to say simply, okay, fine. I don't mind. I know that my domain is just the union of these two pieces with this interface, this overlap. So what I will do, if you ask me to solve the Laplace equation in this domain, what I will do is I will just first solve it in the disk, or you can start also on the other side. This doesn't really matter. How do you initialize, right? You solve it in the disk, for which you have a very nice green representation formula using radial coordinates. And this will give me the first approximation in the disk. The first approximation on the disk gives me also the first approximation on this, common part. And this first approximation on the common part gives me also the boundary trace over here. So in this way, I will have the boundary conditions on the rectangle. And with this, I will be able, using Cartesian coordinates, be able to solve the equation of the rectangle in Cartesian coordinates. Because I have the solution in the whole rectangle, I will have the solution in the yellow interface. And this gives me, in particular, the values of the solution on this arc. This arc here, right, is the boundary of the disk. Having the boundary of the disk, I can apply again, the resolution of the Laplacian using radial coordinates here, and in this way I can alternate, This is domain decomposition. This is domain splitting. So this is the principle that you can divide and conquer, but be careful. If you want to compute really the approximation of this solution, you have to alternate and iterate. So you split, alternate, and iterate, right? You can do the exercise. You can just do it yourself in, you can just do it in, if you want to, in MATLAB, right? And you see what happens. So I can do, so this is artistic computing now, what we are doing, right? So this is not, scientific computing, but artistic computing, right? So I divide the domain into two pieces. I put some overlap, right? And then what I'm doing is I'm writing the segment as the union of this yellow segment and this blue segment, right? With an interface which is this narrow green piece. I can make it narrower or larger, right? Okay, I'm solving in this domain, right? 0L. I solve the Laplace equation with boundary condition 0. So what I'm doing is I'm taking a beam, right, or a string, pushing up with force 1, and then I know what the solution is, right? This is the true solution. It's just one parabola, right? Vanishing in 0 and in L. Now you do domain decomposition in this context of artistic MATLAB. What do you see? You do the first iteration and you see this. Right? Why? Because I have taken the domain 0L, right? And in the domain 0L, I have 0 boundary conditions here. But what do you see? Now, when you move to the second segment, right, to the blue segment here, you take the boundary condition that the left solution is giving you on the right domain. So the second arc does this, because it's taking this boundary condition. Okay, so this was just one solution in one side and one solution in the other. As we said, this is never sufficient because you don't see yet enough the interaction of the two phenomena, although there was some thanks to this green interface. Just do one further step. What do you see? What you see is that now, right, the blue solution is giving you the boundary value, right, on the new left yellow computation. And then you get something like this. And now when you get to the next step, you go back to the blue side, you take the boundary value here in the extreme, of the blue segment, which is inherited from here, and then you get something. And then in the next iteration, right? And in just a few iterations, you will not, human eye will not make the distinction between the true solution and the, a split iterated domain decomposition solution. Okay, so this is artistic domain decomposition for you. Exercise, just try to do it in MATLAB. If someone does it, please, you can bring the picture and tomorrow you put it in the chat. We will observe that indeed, in a few iterations, this is the magic of scientific computing, is that, theoretically we will prove some polynomial or exponential, maybe asymptotic convergence when the number of iterations goes to infinity. This is what the theory will give you, some convergence as n goes to infinity. The beauty, one of the beauties, not only analysis, is also that in practice, this works much better so that in a few iterations you see it, okay? And then what Lee splitting says is that the exponential of A1 plus exponential of A2 is the limit as n goes to infinity of exponential A1 over n, exponential A2 over n, exponential A1 over n, exponential A2 over n, okay? Meaning that indeed, you cannot say that exponential A1 plus A2 is just the iteration of exponential A1 and exponential A2, but if you carry it in pieces and you alternate, you split and you alternate, then asymptotically, as n goes to infinity, you will see the superposition effect, right? Okay? The bracket will emerge. The bracket that makes, the cross effect of A1 plus A2 modify the dynamics that you will get separately by A1 and A2. You need, of course, in theory, n go to infinity, but in practice, of course, you can apply this with n large, but not going to infinity, and you see already, the cross dynamics emerging.